Assalamu alaikum everyone. Welcome to the course of ME212 Dynamics. This is lecture 29 and today we will start a new topic which is instantaneous center of zero velocity. So in this lecture we are looking for analyzing the general plane motion by another method which is finding out the instantaneous center of zero velocity. So let us say that you have a cylinder which is rolling on a surface and this is rolling without slipping. It is rolling without slipping. So this is the contact point between the surface and the cylinder. So at this contact point, as this cylinder is rolling without slipping, so here the velocity is equal to 0. As the surface, so the velocity of the surface is 0, so the point which is in contact with the surface also has a velocity 0. So it means that this cylinder is rotating about this point. That is, cylinder is rotating about this point. Which point? This is the point which is the at contact of the surface and the cylinder. So cylinder is rotating about this point, or at this instant it seems that cylinder is rotating about this point. So why I am saying that the cylinder is rotating about this point? Just recall that we have a velocity VB equal to velocity of VA plus velocity of VB with respect to A, where B and A are the any 2 points on the rigid body. So imagine that the velocity of the point A is 0. So when the velocity of point A is 0, so the velocity of the point B, a particle B, become VB with respect to A, which is equal to omega cross RB with respect to A. So what is this equation? This equation is for rotation of a rigid body about fixed axis. So when this equation it only come when the velocity of the particle A is 0 or when there is no translation. When the velocity of the particle A is 0, the velocity of the particle B equal to omega cross R B with respect to A. So in the present case, as the velocity of the particle, as the velocity of the point which is at contact of the surface and the cylinder is 0, so we can call this as a cylinder is rotating about this point. As earlier we derived this equation for the rotation of rigid body about fixed axis. The same is true for the present case. So when the body rotate about any fixed axis, so the axis has to pass through the point A. As in this case RB with respect to A means as the velocity of the particle A is 0, the axis RB with respect to A has to pass from the point or particle A. So in the present case, as the velocity of the contact point is 0, so there when we have to find the velocity of any other point on this rigid body, then the position vector has to pass through this contact point. Let us say that you have to find out the velocity of the particle. Let us say that this is the particle B. So what will be the velocity of this particle B? The velocity will be tangent to this circle or tangent to the path. So what is RB with respect to this contact point? This is RB with respect to the contact point, and it act in this direction. So this velocity is equal to omega cross R. Let us say that this is R. So this velocity V is the cross product of omega and R, and it has to make a 90-degree angle with this position vector, as the velocity is perpendicular to the plane containing omega and R. So the velocity has to make an angle of 90 degree with the position vector, and it has to be tangent to the path. So this instantaneous center, so this is called as this contact point is called as the instantaneous center of zero velocity. So it keeps on changing with time. So at the present instant, this is the instantaneous center of zero velocity. So at time t plus delta t, there may be another instantaneous center of zero velocity about which this body is rotating. So this is all about the instantaneous center of zero velocity. Now what will be the location of instantaneous center of zero velocity? Here IC stand for the instantaneous center of zero velocity. So velocity, let us say that there is a point A. Let us say this is the point A. So the velocity of this point A is known to us, which is VA. So how can we find out the instantaneous center of zero velocity? So this velocity is always perpendicular to the relative position vector, which is RA, with respect to instantaneous center. So it is always perpendicular to the relative position vector, which is starting from the instantaneous center of zero velocity and end at point A. So instantaneous center is always located at a perpendicular position vector from the velocity. So as we know that VA is equal to omega cross RA with respect to the instantaneous center. So what is RA with respect to instantaneous center? RA with respect to the instantaneous center is equal to VA over omega. So in this way we can find out the position vector with respect to instantaneous center, or we can also find out omega of this rigid body, about the angular velocity at which this rigid body is rotating. So there are the different cases for finding out the instantaneous center of zero velocity. In the first case, let us say that you have a 2 point, let us say that point A and point B on the rigid body. So the velocity of the point A is VA and the velocity of the point B is VB. So how can you find out the instantaneous center? So from the point A, you have to draw the perpendicular position vector, a perpendicular line. Just say that you draw the perpendicular line from the velocity VA, and this line is, let us say that this is the line, and the from point B also draw the perpendicular line. So the point at which these two perpendicular lines meet, this is your instantaneous center of zero velocity. This is the case when you have 2 points on the rigid body and the velocity and the direction of the those two points on the rigid body are different. And the second case is when you have 2 points on the rigid body and the velocity are anti-parallel to each other. So in the first case, let us say that on the point A the velocity is VA, on the point B the velocity is VB. So how can you find out the instantaneous center of zero velocity? So by proportional triangle rule you can find out the instantaneous center of zero velocity. So the third case is when you have a velocities at 2 different points and the velocity are different in magnitude but same in direction. So in this case you can find out the instantaneous center of zero velocity by similar triangle rule. So if the velocity magnitude are equal and the velocity vectors are parallel, the instantaneous center of zero velocity is infinity and the angular velocity in this case is 0. So this is the case when the instantaneous center of zero velocity is located at infinity and angular velocity becomes 0. So this will be the case of simple translation. In case of the rotation, the instantaneous center of zero velocity must be at a finite distance and angular velocity must not be equal to 0. So this is the 3 case for finding out the instantaneous center of zero velocity. So let us look how can we find out the instantaneous center of zero velocity in a real world problem. So this is example 16-10. Determine the location of instantaneous center of zero velocity for the member BC shown. So in this example we have to find out the instantaneous center of zero velocity for the member BC. On the member BC we have 2 particles. First particle is particle B and the second one is particle C. As the particle C is on the piston, so the piston is constrained to move in the horizontal direction in this case. So what will be the velocity of the particle C? The velocity of the particle C will be horizontal VC. So what will be the velocity of the particle B? As the particle B has to move in this trajectory in the circular path. So what will be the velocity of the particle B at this instant? It will be tangent to this trajectory. This will be the velocity of particle B. So how can we find out the instantaneous center of zero velocity? So instantaneous center of zero velocity can be found out by drawing the perpendicular to both the velocities. So by drawing the perpendicular to both the velocity, we can find out the instantaneous center of zero velocity. So as I discussed in the previous slide that on the particle C we have the velocity Vc, on the particle B we have the velocity Vb. So how can we find out the instantaneous center of zero velocity? We can find out instantaneous center of zero velocity by drawing the perpendicular to both the velocities. So let us say that the perpendicular to Vc is this one and the perpendicular to Vb is this one. So the point at which these two perpendicular meet with each other is your instantaneous center of zero velocity. So from the instantaneous center of zero velocity we can draw the position vector on the particle B and particle C, and the position vector on particle C is RC with respect to IC and the position vector on particle B is RB with respect to IC. So in this case how can we find the velocity of the particle B? The velocity of the particle B will be equal to omega cross RB with respect to IC, and similarly velocity of the particle C will be omega cross RC with respect to IC. Remember that the angular velocity is independent on the reference point. So omega is independent of reference point. So this is the what is instantaneous center of zero velocity? This means that this rod BC rotate about this instantaneous center of zero velocity with the velocity with position vector RBC and RC with respect to RB with respect to IC and RC with respect to IC from the two particle B and C, and with an angular velocity omega. You can call this as angular velocity omega BC, omega CB, or omega, as omega is independent of reference point. So it does not matter whether you can write it with respect to B or with respect to C. So again, in this example, we have to find out the instantaneous center of zero velocity for the link CB shown. So in this example, this is the particle C and this is the particle B on the link, and we have to find out the instantaneous center of zero velocity at this instant. So as the particle C move along this trajectory along this circular path with a velocity, particle B also move along this path with a velocity. So what will be the velocity of the particle C? The velocity of the particle C will be tangent to this path. So velocity of the particle C will act downward. Similarly, the velocity of the particle B will also act downward. So if I draw this link separately, so this is our link CB. On this, the velocity VCA and VB act downward. So we for finding the instantaneous center of zero velocity, we have to find out we have to draw the perpendicular on VC and VB. Let us say that the perpendicular on VC is, let us say that this is the perpendicular, and similarly the perpendicular on VB is this one. So as the two velocities are parallel to each other, are in the same line, so they will meet with each other. The perpendicular of these velocity will meet with each other at infinity. So in this case, RC with respect to IC will be infinity and RB with respect to IC will be at infinity. So when the two velocities are the instantaneous center of the two velocities are at infinity, in that case omega will be equal to 0. Also when the omega will be 0, the rotation will be 0 and the body only translate. So in this case, when the instantaneous center lie at infinity, so omega become equal to 0 and the link only translate. So this is another example for finding out the instantaneous center of zero velocity. So this is the practical example 16-10 from your book. The statement of the example is block D shown in this figure moves with a speed of 3 meters per second. We have to determine the angular velocities of the link BD and AB at the instant shown. So in this case, the velocity of the particle D is given to us. We have to find out the angular velocity for the link BD and angular velocity for the link AB. So as the particle B is at a connection between link AB and BD, this means that for the link AB and BD, for both the links, the velocity of the particle B will be same. So what is the direction of this velocity B? As this velocity B is the link AB only rotate about the axis which is passing through the point A. So this means that the velocity will be at a tangent to this path, and it will act at a 90 degree on this position vector. So this will be the direction of your velocity. So if I draw the link BD, so this is the link BD. On this is the particle D, this one is the particle B. On the particle D, the velocity is act in the horizontal direction, which is VD, and on the particle B, the velocity act downward, which is VB. This is the velocity on the particle B. So in this case, how can we find out the instantaneous center of zero velocity? So the instantaneous center of zero velocity can be found out by drawing the perpendicular on both the velocity. So let us say that on the particle D, if we draw the perpendicular, so this one is your perpendicular. On the particle B, if we draw the perpendicular, so this will be your perpendicular, which make an angle of 90 degree with VB, and this make an angle of 90 degree with VD. So the point at which the two perpendicular meet with each other, this is our instantaneous center of zero velocity. So the position vector from the instantaneous center of zero velocity, let us say that position vector is, this is the position vector which is RB with respect to instantaneous center, and this is the position vector which is RD with respect to the instantaneous center. So as it is given that this VB is making an angle of 45 degree from the horizontal as it is given here. So what will be this angle? This angle will also be 45 degree. So how can we find out the magnitude of RB with respect to IC and RD with respect to IC? So by using the geometry rule, we can find out, by using the trigonometry, we can find out RB with respect to IC and RD with respect to IC. So what is tangent of 45 degree? So tangent of 45 degree will be RB with respect to IC over 0.4. You can take this as a right angle triangle having this 45 degree. So this will be your 0.4 meter. This length is 0.4. So this will be your RB with respect to IC, and this will be RD with respect to IC. So in this way, it can be easy for you to find out RB with respect to IC and RD with respect to IC. So from this, RB with respect to IC will be equal to 0.4 times tangent of 45 degree, which is equal to 0.4 meter. Similarly, RD with respect to IC will be equal to, you can find out by using the cosine rule. So by using the cosine law, you can find out the RB with respect to RD with respect to IC. So cos of 45 degree equal to 0.4 divided by RD with respect to IC. So this implies that RD with respect to IC equal to 0.4 divided by cos of 45 degree, which is equal to 0.5657 meter. So after finding the position vector of the particle B and particle C with respect to IC, we can find out the velocity of the particle B and particle D. So the velocity of the particle B will be omega time RB with respect to IC, and the velocity of the particle D will be omega cross RD with respect to IC, or RD with respect to IC into omega in magnitude form. So after finding out the instantaneous center of zero velocity, we can find out the velocity for the particle B and the velocity for the particle D. So velocity for the particle B will be equal to omega BD time R B with respect to IC. Here I write omega BD as we find out the instantaneous center of zero velocity for the link BD. That's why I write omega BD. And similarly, omega D VD equal to omega BD time RD with respect to IC. So in this case, VB is unknown, omega BD is unknown. RB with respect to IC is known to us, RD with respect to IC is known, similarly VD is known. So in this case, the unknown are 2, also the equation are 2, so we can find out the unknowns. So in the second case here, the unknown is omega BD, and VD and RD with respect to IC are known to us. So by using this equation, omega BD equal to VD over RD with respect to IC. What is VD? VD is basically 3 meter per second. So this will be 3, and what is RD with respect to IC? It is 0.5657. So it is equal to 5.3 radian per second, omega BD. So it will act in the counterclockwise direction, and we find out this by using the right hand rule. In this case, how can we find out this right hand rule? As the velocity is in the VD is in horizontal direction, so omega has to make an angle of 90 degree with a plane containing VD and D with respect to IC. So by using right hand rule, you can find out that it will act in the counterclockwise direction. So in the similarly, we can find out the velocity of the VB. So velocity of the VB equal to omega BD time RB with respect to IC. So it will be equal to 5.3 times 0.4, which is equal to 2.12 meter per second. This is VB. So in the numerical statement, we have to find out the angular velocity for the rod BD and rod AB. So till now we find out the angular velocity for the rod BD or link BD. So how can we find out the angular velocity for the rod AB? So let us say that this is the rod AB or link. This is the particle B, this is the particle A. So this particle has to move in this direction on this curve. So what will be its velocity? Its velocity will be tangent to this path. So this velocity will be tangent, and this is given as 0.4 meter. So here in this case, this is the case of only the rotation. So for the rotation, we have VB equal to omega cross RB with respect to A. So here the omega will be omega AB. So VB is given to us, which is 2.12 equal to so this can be written as omega AB time RB with respect to A in the magnitude form. So omega AB equal to 2.12 divided by 0.4, which will be equal to 5.3 radian per second, and it act in the clockwise direction. So direction can be found out by using the right hand rule. So in this way we can find out the velocity for the angular velocity for the link AB and BD. So this is the way how can we use the instantaneous center of zero velocity for finding out the velocities, for finding out angular velocity. You can also use this for finding out velocities and acceleration. So in the previous lecture we find out the velocities and acceleration or angular velocities of the links by using the equations that we derived. So you can use either that way or by using the instantaneous center of zero velocity. So this is example 16-12 from your book. The statement of the example is the cylinder rolls without slipping between the two moving plates E and D. So here the two plates are, this is the plate E and this one is plate D. So this cylinder roll between the two plates E and D, and this is rolling without slipping. The main thing here given is rolls without slipping. So we have to determine the angular velocity of the cylinder and the velocity at its center C at the instant shown. We have to find out angular velocity for the cylinder and the velocity for the center of the cylinder. So here it is given that this cylinder roll without slipping. So the velocity of the plate E is given as 0.25 meter per second, and the velocity of the plate D is 0.4 meter per second. And it is given the statement that this cylinder roll without slipping. So this means that the point A, which is in contact with the plate E, and the point B, which is in contact with the plate D, has the same velocities as the plate E and plate D. This means that the point A has a velocity of 0.25 and point B has a velocity of 0.4 meter per second as this cylinder roll without slipping. So the velocity of the particle A will be 0.25 meter per second, which act in the positive x direction, and the velocity of the particle B will be 0.4 meter per second, which act in the negative x direction. So as the two velocities act in the anti-parallel to each other, so we can find out the instantaneous center of zero velocity by the proportional triangle. So by drawing the similarly by joining the head of the two velocities with each other, the point at which it intersect with the vertical line, this will be your instantaneous center of zero velocity. So from the instantaneous center of zero velocity, the position of the particle B will be, we have to draw the position vector. So this is the position vector, which is RB with respect to IC. So what will be the position vector for the particle A? So you have to draw from the IC, this is your RA with respect to IC. So what will be the velocity with respect to IC? So VB equal to omega time RB with respect to IC in the scalar form or in the magnitude form. So what is RB with respect to IC? Let us say that which is given as x. So what will be the velocity for the particle A? So VA will be omega time RA with respect to IC. So let us say that RB with respect to IC is equal to x. So what is RA with respect to IC? this will be 0.25 minus x. So this will be equal to omega time 0 VA will be equal to omega time 0.25 minus x. So the two equations that we got is 0.4 equal to omega x and the second equation is 0.25 equal to omega time 0.25 minus x. So we have two equations and the two unknowns. One unknown is omega and the second one is x. So from these two equations we can find out omega and x. So after solving this, we get x equal to 0.1538 meter. So by substituting the value of x in any of the above equation, let us say that we substitute it in VB equation. So 0.45 equal to omega time 0.1538. So here the omega become 2.6 radian per second and it act in the clockwise direction. So this is the first part in which we have to find out the angular velocity for the cylinder. So in the second part of this statement is we have to find out the velocity of its center C. So for the velocity of for the center C, we have to draw the position vector from instantaneous center to the center C. So let us I first rub this thing so that this become clear to you. Okay, now let us say that this is the point C. So we have to draw the position vector from instantaneous center to point C, which is RC with respect to IC. So what is the velocity for this particle C? Omega VC is equal to omega time RC with respect to IC. So what is the value of RC with respect to IC? So as the given we are given that x is equal to 0.1538 that we find earlier. So from the point C the radius is 0.125. So x minus 0.125 equal to RC with respect to IC. RC with respect to IC equal to x minus 0.125, which is radius. So x given is 0.1538. So RC with respect to IC is become equal to 0.1538 minus 0.125. So in this way VC become equal to 0.0750 meter per second. In this way you can find out the velocity for any particle on the rigid body by using the instantaneous center of zero velocity.